Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis, taken by Professor Krishna P. Kaliappan from Department of Chemistry, IIT Bombay. So this is our ninth week tutorial session, and so far we have seen up to week 6 lecture contents, and we have discussed about the various mechanisms and reactions which were discussed in the lecture contents. Also, we have solved up to this week 5 assignment. So today we'll be starting with week. So today we will be starting with this week 7 lecture contents, which was lecture 30. So before that, we will wait for a couple of minutes to see anybody else is joining. Then we will start with our discussion. So I am Sri Lakshmi. Yes, I am a fifth year PhD student in Department of Chemistry, IIT Bombay. I am working under Professor Krishna P. Kaliappan. Okay, so let's start. So we will be starting with the first lecture, lecture 30 about reserpine. So in this lecture, we have seen the application of Diels-Alder reaction, Bischler-Napier-Elsky reaction in the total synthesis of reserpine by Woodward's group. So reserpine, as we can see in the structure here given, is a pentacyclic compound, and it is isolated from dried root of snake root, which is used in the treatment of snake bites. And the first total synthesis was reported by Woodward's group in 1956. And this is one of the most complex natural product of its size. As we can see, it is having five contiguous stereo centers, five contiguous stereo centers out of six. Out of the total six chiral centers present, then 21 atoms are arranged in five rings. Then a six-membered ring is attached with another six-membered ring with cis ring junction, which can be found by Diels-Alder reaction, of course. And the other key reactions which they used includes this MPV reduction, Bischler-Napier-Elsky reaction, and the starting material they used is benzoquinone. So that's about the total synthesis of reserpine. Next molecule was this yohimbine, and there we have seen the application of Diels-Alder reaction in the total synthesis of yohimbine by Tamerlan group and intramolecular Michael addition in the total synthesis by Momos group. So it is having the same core structure as that of reserpine, which we saw here, and it is isolated in 1880 from this Corinanthe yohimbi. And this first total synthesis was reported by Van Tamerlan in 1958, which is a racemic total synthesis, and asymmetric part was done by resolution. So this is almost similar to the Woodward's total synthesis of reserpine, and he utilized butadiene and benzoquinone as the starting material. And they completed this total synthesis in 20 steps with 0.024% of overall yield from the Diels-Alder adduct. And the Momos total synthesis in 1990 it was published, and it is the first formal asymmetric synthesis. And here the key steps include asymmetric intramolecular Michael reaction, and he used the starting material as protected benzylamine. And this Momos group synthesized this molecule in 13 linear steps with 25.6% of overall yield. Now, the next discussion was about quinine. And here we have seen the first formal total synthesis of quinine by Woodward's groups following Rape's protocol and Stokes asymmetric total synthesis. So this quinidine are cinchona alkaloids which are isolated from the barks of cinchona and remigia species, and they are used in the treatment of fever. And especially this quinine is having anti-malarial, antipyretic, analgesic, anti-inflammatory activities. Though quinine was not structurally complex compared to many other complex natural products isolated now, due to the lack of techniques, it took long time to arrive at its correct structure. Degradation studies were carried out to assign partial structure. Pasteur in 1853 demonstrated that this quinine, naturally existing quinine, is levorotatory. So the empirical formula was dem- uh, put forward by Strucker group in 1854. And this degradation studies on quinine formed this quinotoxin, meroquinine, methoxyquinol derivatives. So the structure of quinine was put forward by or discovered by Paul Rabe in 1907, and the first partial synthesis was done by Paul Rabe in 1918, and the first formal synthesis was done by Woodward's group in 1944, and the first stereoselective total synthesis was done by Stork in 2001. So, in the Woodward's formal synthesis, the starting material they used was meta-hydroxybenzaldehyde, and he synthesized up to quinotoxin, which was already converted into quinine by Doring's group. And Mannich reaction was one of the key reaction which they used in this step, in this total synthesis, and is for the Stokes first asymmetric total synthesis. So Stoke was the first one to do an asymmetric total synthesis of quinine, which was completed in 2001, and they completed the synthesis in 13 steps with 18 percentage of overall yield. Okay. Now the next molecule was dendrobin, where we have seen the application of silver ion mediated cyclocondensation in the total synthesis of dendrobin by Livinghouse, radical cyclization in the total synthesis by Shah, and Posenkan reaction in the total synthesis by Zad group. So dendrobin, as we can see from the structure, is having seven chiral centers, out of which six are contiguous, and then it is having a six-membered ring. And this molecule is isolated in 1932 from a Chinese ornamental orchid named as Dendrobium nobile. So the Living House did this concise total synthesis of plus or minus dendrobin in 8 steps from 2-methyl cyclopentuene 1-ol. And the key reaction employed was silver ion mediated cyclocondensation of isonitrile with acyl chloride. And in Shah synthesis, the starting material used was carbon, and they have synthesized enantiomerically pure dendrobin based on alpha carbonyl radical cyclization, and they completed this total synthesis in 19 steps. Now, for the Zart's total synthesis, which came out in 1999, a chiron approach was utilized from Merbinon, radical mediated ring opening, then Posenkan reaction to construct two five-membered rings, and they also took 19 steps to complete the total synthesis of dendrobin. Now, for the next molecule, which is morphine, we have seen the application of Diels-Alder reaction, Michael addition, and Woodward opener oxidation in the first total synthesis of morphine by Gates. So, the morphine was first isolated in 1806 from opium produced by the cut seed pods of Poppy papaver somnifera. And as we can see from the structure, it is having three six-membered rings, one dihydrofuran ring, and five contiguous stereogenic centers. And the Robert Robinson in 1925 proposed its correct structure. Then Gates confirmed by first order synthesis in 1952 by X-ray and by X-ray in 1955. So the some of the natural opiates include morphine, codeine, thebaine, oripavin, and then Gates and Schudy reported the first total synthesis of morphine in 27 linear steps. And here the key reactions were open or oxidation, Diels-Alder reaction, and the starting material used was naphthalene 2,6-diol. And they completed this total synthesis in 27 steps with 0.0010 percentage of overall yield. Now, for Overman's total synthesis, which came out in 1993, the key reaction was intramolecular Heck reaction to forge the critical quaternary center of morphine skeleton, sequential iminium ion allyl silane cyclization, and the starting material used was isovanillin. And here they could complete the total synthesis in 10 steps with 1.01 percentage of overall yield. So that's about week 7 lecture topics. Now we will see some of the mechanism of the reactions which we discussed in this week 7 lecture. Then we will go to the problem solving. So before that, maybe you can quickly go through this lecture contents and then we will start the discussion of mechanisms. Hello. Okay. So now about this Bishler-Napier-Elsky cyclization. So this is the cyclization reaction using POCl3 in toluene condition. So what is happening here? This amide compound will undergo the cyclization reaction to form this quinolines. So we have already discussed the mechanism of this. So I will not go through it. You may quickly go through it. Then we will go to the next reaction. Now going to the next reaction, intramolecular Heck reaction. I think all these reactions we have discussed previously. Okay, so these all reactions we have seen, intramolecular Heck reaction, Oppenauer oxidation, then Mervyn Pondorf Worley reduction. And this managed reaction also we have seen the mechanism previously. Okay, now let's move on to the week 6 assignment question. So the first question is, identify the major product in the following transformation. Okay, I just remember now that we have already discussed this week 6 assignment in the last session. Yeah, this we have already discussed. And let me just clarify where we were in the last session, then we will continue the session. Okay, so in the last session we have already discussed this week 6 assignment and then lecture 36, 37, 38, 39. So I think we have discussed up to here this epibacterium. Okay, so today now we will start with the discussion on Mitsunobu reaction first, and then we will see what is the mechanism of this Staub condensation reaction and this Beckmann rearrangement, then Robinson annulation, a Saprin's reaction, alkyne Zipper reaction. So there are quite a number of reactions. We will be familiar with the mechanisms by today. So for the Mitsunobu reaction, it is basically the reaction between an alcohol and an acidic compound with a substituted product. So in the we will be getting a substituted product in the presence of this PPH3 and diethyl or diisopropyl azo-dicarboxylates. So this is the mechanism. So what is happening first? This PPH3 will attack over this nitrogen, and this bond will shift over here, and this oxygen bond will shift to this oxygen. So that will form this intermediate. Then when this oxygen lone pairs will come back, this double bond will take the proton of the other reactant and it will form this intermediate. Then this oxygen, which is our starting material alcohol, so that alcohol oxygen is having affinity towards this pph3, so that will take this pph3, so this bond will come over here and this will shift to here to form this intermediate as well as this intermediate. Then this will again take the proton of this alcohol to form one of the byproducts, that is diethyl 1,2 hydrazine dicarboxylate. Then this molecule, what is happening, this oxygen lone pairs will fall over here and this will form, then pph3 oxide will eliminate, nucleophile will attack over this carbon center to form this other byproduct triphenyl phosphine oxide and this substituted product. So it is basically like a condensation reaction, we can say. OH is leaving from alcohol and from here H is leaving. So the byproducts we are getting are diethyl 1,2 hydrazine dicarboxylate and triethyl phosphine oxide along with the substituted product. So this is an example for SN2 reaction. So we will be getting the product with inverted stereochemistry. Now going to the next reaction, which is stop condensation reaction. So here we have an aldehyde or a ketone. Then this dialkyl succinate in the presence of base in solvent, it is forming this compound, which upon acidification we are getting this alkylidine succinic acid monoalkyl ester. So what's happening here? So first, this base will take the proton of this dialkyl succinate, and that will form this ester enolate kind of intermediate, and this will come back, and this enolate will attack over this carbonyl carbon of this aldehyde or ketone, which will form a beta alkyl oxy ester. Then an intramolecular acyl substitution is happening. So this O minus, which is from our aldehyde or ketone, is attacking over this carbonyl carbon center, and it's forming the cyclic kind of intermediate. Then this OR3 minus will take the proton from here, this position. So this OR3 minus is leaving, this oxygen lone pair will come over here. OR3 minus will leave and it will form this intermediate. Then that OR3 minus will take this proton. So this will shift and this ring will open. This gamma electron will open to form this intermediate, which is written like here. And then hydrolysis will give the corresponding carboxylic acid. So from this dialkyl succinate and an aldehyde or ketone, we are getting alkylidine succinic acid monoalkyl ester. So this reaction is known as stop condensation reaction. Now the next reaction is Beckmann rearrangement, which is the acid catalyzed rearrangements of ketoxime to form amide. So here what is happening? Firstly, this ketoxime will get protonated and then water molecule will leave to form this kind of intermediate. Then again water molecule will attack over this carbon and then proton loose will form this one. Then this nitrogen will take this proton and then this proton will leave to form this corresponding amide. So it is the acid catalyzed conversion of oxides to amides. Now, the next reaction is Robinson annulation. This also we have already discussed previously. So, it will be happening by first the deprotonation of the ketone by a base, which results in an enolate, and then conjugate addition of an unsaturated ketone to the enolate, resulting in a new enolate, and then Michael addition is happening. So, this is like Michael addition followed by aldol condensation. We can say we will be getting this Robinson annulation, that is, new ring will be formed in this reaction. Now the next reaction is Asaprin's reaction, where this alkene and this aldehyde or ketone in the presence of acid can give different piperidines, indolizidine, quinolizidine, huperzine, lyconidine, cylindrosines, and cortistatin kind of core structure can be resulted. So what is happening in the presence of Bronsted acid or Lewis acid? Firstly, this intermediate is forming, and then the cyclization will happen to give this compound. Then nucleophile will can attack at this carbocation position to get this compound. So if this is NH, first that iminium ion will form, then that cyclization is happening to form this carbocation, and then nucleophile will attack, and that will give Asaprin's reaction. So this Asa comes from this nitrogen, that is responsible for the formation of this iminium ion. So the next reaction is alkyne zipper reaction. So here what is happening? This hydrazine kind of derivative. is attacking over this alkyne to form this alene kind of intermediate, and then this proton is taken by other NH to form this one, and then again this proton is taken by this NH minus to form this intermediate, and which upon hydrolysis will give this one. So it is just like a migration kind of reaction, we can say alkyne zipper reaction. So it is just the isomerization of internal double bond to a terminal position by utilizing this um, 3 amino propyl amine. Now the next reaction is Cannizzaro reaction. So is that it is that like formaldehyde molecule under basic and heating condition, it is forming this sodium formate. So what is happening first, OH minus will attack over this carbonyl carbon to form this intermediate, and then this will come back, this proton will be like this will attack over, this will come back, and this proton will go to here to form this intermediate, then these two will combine to form this compound, and that can be again hydrolyzed to form formic acid. So it is a redox disproportionation, we can say, between a non-enolizable aldehyde which is lacking an alpha hydrogen in the presence of strong base, yielding one molecule of the corresponding alcohol and one molecule of the corresponding aldehyde, carboxylic acid. Now about this Friedel-Crafts acylation. So one acylating agent, usually acetyl chloride, and then aromatic compound will be there. In the presence of this Lewis acid catalyst, this acyl group get added to the aromatic compound and the byproduct will be hydrochloric acid. So firstly, this AlCl3 will take this chloride and it will form this acylium anion, acylium carbocation, and this benzene ring will attack over this acylium ion to form this intermediate. Then rearomatization will occur to form this aryl ketone. So this is known as Friedel-Crafts acylation. Okay, now we will start this week 7 assignment question. So the first question is identify the major product in the following transformation. So this compound upon treatment with this DBU in benzene, we are getting one product out of this four options. So try to identify which product can form under DBU condition and what will be the mechanism. Okay, so here the correct answer is option D. And what is happening? Firstly, dbu will take this proton and this will attack over here, bromide will leave, and then this will form. Yeah, this will be forming. So here double bond is in this position, so that is also migrating. But here already double bond is given in this position. Maybe starting material is wrong, I don't know. So that is the correct answer is option D. Now the second question is, what is the major product formed in the following transformation? So this compound upon treatment with this methane sulfonic acid and P2O5, which will be the major product here? So here what is happening? This OH will, so this one is attacking over this center and that is undergoing a cyclization kind of reaction, and I think there is some mistake between the starting material. Yeah, it is correct only. So one bromine is extra in the given mechanism, given question, and here that bromine is not there. So what can happen here? It's only possibilities one, two, three, four, five. Here it was like one, two, three, four, five, six, and here it is one, two, three, four, five, six. So two possibilities are there, and here the case is one, like one, two, three, four, five, six. Six membered ring will be forming. That is the only possibility. This side it is already blocked, and this side is will be resulting in 7-membered ring, which will not be favored. So this is an example for Friedel-Crafts acylation, we can say, and we will be getting this compound B as the major product, and the stereochemistry is retained in the starting material as in the product as in the starting material. Moving to the next question, identify the major product in the following transformation. So this compound is treated with FeCl3 HCl in water and then SO2 methanol in water, which will be the major product. So here, what is happening? So, firstly, this compound will get converted into this. So, the correct answer is this one, option B. So, this is a kind of, we can say, substitution kind of reaction. So, firstly, this alcohol will be converted into this one in the presence of FeCl3 and HCl. Then, in the presence of SO2, this one of this alcohol, yeah, then in the presence of this SO2, this will be converted into this diol kind of derivative, like phenolic kind of compound. Now the next question is, which is the major product formed in the reaction given below? So this compound upon treatment with MCPPA DCM in the first step and then titanium tetraisopropoxide in the second step, which will be the major product? So here what is happening, first MCPBA will form epoxide as we know on this double bond. Then this epoxide will be opened by this titanium isopropoxide, and this epoxide formation will be directed by this alcohol. So the epoxide will be formed in the same phase as that of this alcohol. Then titanium isopropoxide is a Lewis acid. It mediated epoxide ring opening. Here proton will leave and this bond will shift over here, and this will come back, this will come over here to form this compound. So the correct answer is option C. So this OH and this OH stereochemistry will be the same. Now the next question, which of the following reagents would carry out the following transformation? So this compound is converted into this lactone, not lactone, this cyclized product. So which will be the condition for that? So first option is diazomethane, then COCl2, then rhodium acetate. Second is diazomethane, then rhodium acetate, and then COCl2. Third option is COCl2, diazomethane, then rhodium acetate, and last option is COCl2, rhodium acetate, and then diazomethane. Okay, so here the first option is oxalyl chloride, then diazomethane, and then rhodium tetraacetate. So what is happening? First, oxyl chloride will convert this carboxylic acid into corresponding acid chloride. Then diazomethane will convert that into this particular what diazo compound, and then rhodium acetate mediated cyclization at the center will take place to form this compound. So the correct answer is option C. Now the next question, which of the following reagents would carry out the following transformation? First one, methyl chloride, triethylamine, then H2O2, then tosyl chloride, triethylamine, H2O2, then NaOH, then Mitsunobu reaction, and then NaOH. So here the correct order is this: first Mitsunobu reaction will take place at this center, so that will reverse the stereochemistry of this alcohol. So they are doing this Mitsunobu reaction with benzoic acid, so that will create O and that benzoate derivative with the opposite stereochemistry. Then NaOH will hydrolyze that benzoate ester to form this corresponding alcohol with the opposite stereochemistry as that of the starting material. So we have already discussed the mechanism of the Mitsunobu reaction, so I am not going to that. Now the next one is identify the major product formed in the reaction given below. So here, firstly, this compound is treated with this BH3, borane dimethyl sulfide complex, and then H2O2 in NaOH. So which will be the major product formed here? So this is an example for hydroboration oxidation reaction, where this double bond will also get converted into the corresponding alcohol, and this ketone will also get reduced by this BH3DMS to form this alcohol. So here first step is hydroboration of this double bond, so that will form this one. Then in the presence of H2O to NaOH, this will be replaced by OH, and this ketone will be reduced into alcohol as well. So the correct answer is option D. Now the next question is, identify the major product in the following transformation. So this compound upon treatment with the samarium iodide in THF at RT, which will be the major product here. So here what is happening, the samarium iodide mediated cyclization is happening. So samarium iodide is basically a single electron donor. So that will form a radical at this center, and then this homolysis with this double bond cleavage, and then this radical reaction can result in this cyclized product, and followed by the lactonization can result in this compound A. So the correct answer is option A. So this is only without lactonization, and if that is also happening, we will be getting this one. Now the next question, identify the major product of the following reaction. So this compound upon treatment with this one in the presence of this potassium tertiary butoxide, which will be the major product formed here. So here what is happening? This first potassium tertiary butoxide will abstract proton from this sender. This will attack over here and then this will attack over this one and this will leave to form this epoxide. So the correct answer is option B. And the next question, identify the major product in the below reaction. So this compound upon treatment with AIBN and tributyl tinhydrate in toluene heating condition, which will be the major product. So here what is happening in the presence of this AABN and tributyl tinhydrate, here this bond will undergo homolysis and here radical will form, here radical will form, that will combine with nitrogen to form this intermediate and then this will open to form this one and this can get quenched to form the corresponding product, which is option C. So this is an example for radical cyclization reaction. So the strain associated with the cyclobutane ring is the reason for ring opening. So that's it about today's session. So remaining we will continue in the next Saturday session. So if you have any doubts or any questions, please do let me know. Thank you for joining. I hope it's all clear. Thank you. We'll see you in the next session.